Hello. In this module, we are going to revisit thermodynamic equilibrium and we'll establish how the concept of equilibrium helps us to describe a system or a flow state. We'll also explore a calculus theorem called Taylor's theorem and how it helps us build relationship between properties. So let's begin with an animation. In this animation, we have a system, a composite system described by this red boundary. It has two subsystems A and B. Let's consider A is a gas at a pressure 400 kPa, B is another gas at a pressure 100 kPa. If this pin is removed, we pretty much know what's going to happen. So let's play the animation and then discuss this a little further. Well, the piston is going to move back and forth and is going to come to an equilibrium where the two sides will have the same pressure. And this is known as mechanical equilibrium. We all intuitively understand that. Similarly, so this internal wall is like an internal constraint. If there is a pinning that pin keeps the piston in position, then it's possible to have difference in pressure. But if you loosen that constraint, if the pin is removed, the pressure difference is dissipated, and ultimately mechanical equilibrium is achieved when these two pressures are equal. The same concept goes over to thermal equilibrium. So for instance, if you remove the barrier and the hot and cold blocks are allowed to come in contact, sooner or later the temperature will become equal, and we will say that these two blocks are in thermal equilibrium. Chemical equilibrium is a little more difficult concept. It could be about a difference in concentration. For instance, if you drop a drop of ink in water, or in this case the constraint is removed, means helium is allowed to pass through this barrier. Or even chemical reaction. In this kind of situation, there is a chemical imbalance represented by a function called chemical potential, a property called chemical potential. When that becomes equal, then system comes to what is known as chemical equilibrium. And when all these three equilibrium exist in a system, the system is said to be in thermodynamic equilibrium. Okay, let's proceed and understand equilibrium more. So suppose we have a global system, a dynamic system that we are used to. It has all kinds of interactions and things are changing everywhere. But if you isolate this big system, the global system, we stop any mass transfer, stop all the heat transfer, stop the shaft work, cut off electricity, and when everything's said and done, you will find that the system will come to equilibrium. All the differences between different points in the system will disappear, because in this big system, inside the system, there are no barriers. So if at one point temperature is hot, another point temperature is cold, after some time temperature will become equal. So that's the concept of thermodynamic equilibrium. If you just isolate a system and observe it over a long time, it will eventually come to equilibrium. This can be another case. Suppose there is ice melting in water and suddenly you isolate that, and you will find the ice and water will coexist forever. If there is sufficient ice in water, of course. So this is another example of global equilibrium. But how can that be useful? I mean, in most interesting systems, things are changing. In a turbine, steam is coming, steam is leaving. In a pump, water is entering, water is leaving. Anyway, so you can get the idea. So how relevant is this equilibrium? To understand that, think of this concept that even though in this animation we are showing a global system which is in flux, things are changing everywhere with time, with space, but at any given time, if you quickly isolate some local systems, in other words, in your mind you just scoop them out and isolate them, you will find that their state generally do not change over time. Imagine the concept. Even though the global system is not in equilibrium, what we are proposing that locally these little systems are in equilibrium. That is, if you have a room where one part is heated, one part is cooled, then temperature in your room could be hot at one place, cold at another place. But if you scoop out a little piece of air from anywhere and find the temperature and pressure and isolate it so that nothing else can enter that particular local system, then that pressure, temperature, etc., that describe the local equilibrium is never going to change. This is a very, very powerful hypothesis. There is no proof for that. That's what makes thermodynamics so interesting. Even though the global system is in total chaos, the local system can be considered in thermodynamic equilibrium. So if you study equilibrium, we immediately understand as aggregate of that a lot of stuff about the global state. With that in mind, let's simplify. In this animation, we are showing a system state, a state that is describing the gas inside this piston cylinder device. And notice that the state in the system changes, but one simplification could be that if we take any two local states and assume that at a given time they're described by the same state. In other words, they're in the same equilibrium. Then the system is called uniform, and at a given time the global system can be represented by a single state. So in this compression process, we will say the gas goes from state 1 to state 2, where state 1 is described by pressure, temperature, etc., which are assumed same all throughout the system. So that's a nice simplification. Instead of a complex system for which we have to have millions and millions of local systems, we'll have just a single system describing the equilibrium at a given time. We can extend the concept for a flow state also. If you take a cross section anywhere of this flow, the flow state 2 for instance, you can represent it by a single state if you assume those local states are in the same equilibrium. In other words, the pressure, temperature, etc. that describe the equilibrium at a given point is same across this line, which is a pretty good assumption. So because of this, we can assume the flow is assumed uniform, and because of that, a single state can describe the inlet, and a single state, state 2, can describe the exit. So as you notice, in both system state and flow state, the concept of local equilibrium plays a heavy role because we are assuming that all across the system, for a system state, all the local equilibriums are identical. Similarly, across this cross section, all the local equilibriums are assumed identical so that a single state can describe the flow state. So that means the thermodynamic equilibrium is so important to describe either a flow state or a system state. So we have done that in chapter 1, but let's rehash that concept once again. Our goal is to describe a system state, for instance, thoroughly. In this case, state 1 is the beginning and state 2 is the final state in this heating process that we are seeing. It's a bunch of properties. In this diagram, we are showing a whole lot of properties. They all go together to describe the state at a given moment. So for instance, at a given moment, there are all kinds of properties. The material properties are, as soon as you know the name of the material, they are fixed. So they are not really function of equilibrium. But the thermodynamic properties, P, T, V, U, H, S, please pay close attention. P, T, V, U, H, S will come back over and over again in this chapter to understand them because they describe the thermodynamic equilibrium. Then there's something called extrinsic properties. Extrinsic properties. If you know the thermodynamic properties, you can easily find the extrinsic properties if you know the velocity of the system and the elevation of the system. For instance, the kinetic energy is simply depends on the velocity. The potential energy depends on the elevation. The stored energy, which is U being a thermodynamic property, U plus Ke plus Pe. So you get the idea. So we can establish some general equation where the extrinsic properties are related to thermodynamic properties. Likewise, the extensive, the total property, the total mass, total energy, total volume, etc., can be also obtained from thermodynamic properties if you just know the mass of the system. So for instance, if you know the mass of the system and you know the the specific entropy S, then the total entropy can be found very easily, because you know total entropy of the system will be mass times specific entropy. Similarly, total energy can be found from mass times specific stored energy. And how do you find specific stored energy? If you know Ke and Pe and U. So U is the thermodynamic property, and Ke and Pe are extrinsic properties from velocity and height. We can do the same for a flow state. If you notice, for a flow state also, the material and thermodynamic properties are identical. I mean, they are not identical. What I mean is that they form the same identical core of this extended state or extended flow state. And as you peel different layers, outside we have transport properties. Instead of mass or entropy, we have flow rate of mass at state 1 and state 2. The extrinsic properties again depends on velocity and height. So what I'm trying to say here is that look at the similarity between an extended flow state and an extended system state. The core material and thermodynamic properties they do not change. They are the same set of properties that describe the equilibrium. And we add these outer two layers, one based on velocity and height, and another based on total mass or the mass flow rate of a flow state. So if you peel away these extrinsic properties and system properties, then what is left is called thermodynamic properties. As you can see, the thermodynamic properties are same set for both a flow state or a system state. So that simplifies evaluation of a state tremendously. We don't have to think about a flow state and system state anymore. For any equilibrium, we can just say, let's first find the material properties of the working fluid, working substance, which are, you can Google it or it's given in a table. As soon as you know the name of the material, properties such as molar mass, and these are other properties we'll encounter later on, can be obtained. And then we have all these thermodynamic properties, P, T, V, U, H, S. We have to somehow figure that out. Then we know the equilibrium state of the working fluid. And once we know that, for a system state, we can, if you know the velocity and height, we can find all those green properties. And if you know the mass, we can find all these black properties. Everything is known. So, why is thermodynamic properties so important to evaluate? Well, the beauty of a thermodynamic state is that even though P, T, V, U, H, S, just the 6 properties that I'm supplying here, there are more of those. Even though there are so many of thermodynamic properties, when a system is in thermodynamic equilibrium, then any thermodynamic property is related to any 2 others. In other words, if you know 2 independent thermodynamic properties, there exists a relationship with which you can find all other properties. In other words, suppose we know pressure and temperature, then you can find enthalpy, you can find internal energy, etc. So that's called the state postulate. State postulate means there are only 2 independent thermodynamic properties for a pure substance. By pure substance, I mean when there is only one chemical composition throughout the system, then it's called pure substance. So what I'm saying will not apply to, say, a mixture of, say, salt and water. Well, it's not quite true. What I'm saying is that if salt and water, if all the salt is dissolved, then we'll have the same chemical composition. It can be treated as a pure substance. But suppose there is some salt sitting at the bottom of water, then the system will not be pure. In that case, things become a little more complicated. But in general, whenever you have a pure substance that is the same chemical composition everywhere, all you need are two properties, two thermodynamic properties, and you can find the rest. So how do we go about finding functional relationship between, let's say, enthalpy and pressure and temperature? Well, the problem is that there is no universal function relating those thermodynamic properties. But what happens when you do an experiment, it's very difficult to find the, say, the internal energy of a block of copper. But it turns out that it's easier to find the change in internal energy. Suppose you heat up the block of copper by certain temperature. Then from the heat transfer calculations, you can figure out how much change in internal energy happened. So when you know the change, from there you want to figure out what the functional relationship is. That's where this theorem from calculus called Taylor theorem plays a very important role. What is this theorem? It's very simple. Suppose z is a function of x and y. Notice that that's exactly what thermodynamic variables are, right? It's just like we can say, let's say, enthalpy is a function of pressure and temperature. So you can see that thermodynamic variables are like this. So here we have a z equals function of x and y. Notice instead of writing f, we write z here, so that these are different functions. So if you know the function, it's so easy to find the change, right? dz will be simply z evaluated at x plus dx, y plus dy, minus z at evaluated at xy. If you know the functional relationship, you can calculate change in z very easily from these functions. But problem is that we do not know the functions. That's where Taylor's theorem becomes very handy. The Taylor's theorem says that, well, you can figure out dz, the change in function, if you know the slope of z with respect to y and slope of z with respect to x. What are the slopes? Okay, you understand what I mean is that, so del z del x means when you hold y constant, means slope along this xy plane that we are showing in this animation, and del z del y means slope on the other orthogonal direction. So slopes are nothing, these are partial derivatives are nothing but slopes when you hold, when you set a direction, set a plane. In other words, set the other variable constant. So when we put the x in this denominator as a suffix, we means x is held constant. So just the physical meaning is more important here than the details. So the idea is that if you know these two slopes, then you know a lot about the function. If you know the two slopes, then a change in variable x and y and these two slopes together will tell you how z changes, even though you don't know the function itself. That's a pretty powerful theorem. So these slopes becomes by themselves very important properties in thermodynamics. So for example, U, suppose U is assumed to be function of V and T, U meaning specific internal energy. I'll keep calling it just the internal energy, but from the symbol you should understand which is specific and which is total. Capital E will be the total specific energy. Okay, total internal energy. So U is a function of specific volume and temperature. U is a function of V and T. So just suppose this diagram, this hill represents EU. As you go, T and V are the two axes at the bottom, and U is the vertical axis. So the height of this hill tells you how much U is. So the slope of U with respect to T, as you hold V constant, look at the V constant plane, this itself is a very special quantity. This slope in its own right it plays such an important role in figuring out how U behaves in a system, how to find internal energy, because this will tell you how it changes with temperature. This is called a new thermodynamic property on its own right. It's given a symbol CV because in this derivative V is held constant. And it's called specific heat at constant volume. In my opinion, it's a terrible name because it's not heat. Heat is Q. But it is something related with heat transfer per unit mass. That's how it can be experimentally found. That's the historical reason why it's called specific heat, because we divide by unit mass to calculate this CV. Also, the fact that it's called specific heat at constant volume doesn't mean this property only makes sense when volume is constant. Not at all. I wish this property had a symbol called alpha or something like that. Actually, alpha is used for something else, but any symbol would have been nicer than calling it CV. But we are stuck with the convention. So what is CV? CV is simply slope of U with respect to temperature and volume is held constant. So knowing CV means you know a lot about U now. You know how U changes with temperature if volume is kept constant. Similarly, there is another property called CP, which is the specific heat at constant pressure, which comes from enthalpy expressed as a function of temperature and pressure. And again, it's a slope. And what is CP? It's how enthalpy changes with temperature when pressure is held constant. So CP and CV will become very important properties for us, just like pressure, temperature, V, U, H, S. Okay, now that we have defined CV and CP, let's go and write down a few thermodynamic relations based on Taylor's theorem. So suppose we want to figure out what U is. So we can express U as a function of temperature and specific volume. U can be a function of any two thermodynamic properties. So therefore, the U must be equals del U del T at constant volume dt plus del U del V at constant temperature dV. And that's exactly what CV is. So we can write that as CV dt plus del U del V. So this is always true. So whenever we want to formulate how to find U for a particular group of materials, we'll start from this relationship. So we'll call this the U relation, the property relation to find U. All right, if we do the same thing for enthalpy, but this time we'll express enthalpy as a function of temperature and pressure, and then we can write dH is del H del T, again, standard Taylor's theorem. And then we recognize this is nothing but Cp, so it becomes Cp dt plus dLH del P, temperature at dP. So we'll call it the H equation. These are the differential relation, and that will help us always to find enthalpy relationship. Remember, our goal is to find relationship find the properties P, T, V, U, H, and S. These are the thermodynamic combo that we are after. So we have now a relationship for U, we have a relationship for H, and now what about entropy? Well, without going into a detailed derivation, let me just give it to you. It's called the TdS relation. TdS plus du, TdS equals du plus PdV. It's known as the TdS relation. It's a famous relation. It comes from combining the balance equation for energy and entropy for a differential infinitesimal process where a system barely goes from one state to a neighboring state. Without going into the details, let's just to understand the meaning of it. So if we have two equilibriums very close to each other, the change of entropy is related to change of U and change of specific volume through this relationship. this is known as the first TdS relation. If we manipulate this little bit, suppose we write this as dH, so this is our first relationship. If we write it as du plus PdP plus VdP minus VdP, plus and minus the same quantity, then we use the product rule here. It becomes du of PV minus dV, VdP, then it becomes d of U plus PV, and that's nothing but enthalpy. If you recall the definition of enthalpy, specific enthalpy. So now we get a new relationship called TdS equal dH minus VdP. So this is known as the second TdS relation. So whenever we want to find U, we'll start with U relation. Whenever we want to find enthalpy, we'll begin with the H relation. It's not called equation, it's called relation, I'm sorry. And to find entropy, we're going to use either the first or the second TdS equation. Again, the book has a detailed proof. You can go over that. But the important thing is for you to understand what each number means. So if I have a system, say a copper block, and I heat it up a little bit, just a tiny bit of increase in temperature, then the temperature of this solid block times the change in entropy must be equal to the change in internal energy plus pressure times change in specific volume. Well, so to summarize, what we have learned in these relations is that when you have the thermodynamic properties, suppose a material is given to you, immediately you know the material properties. So to find an extended state of either a system or a flow, first thing to go after is material properties. That's the easiest to find. Material properties means such as molar mass. Let's take that as an example. So if you know the material, suppose I say a system contains nitrogen, or it contains oxygen or copper or water, immediately molar mass is known. You don't need to know anything more. Then comes the thermodynamic property. Okay, thermodynamic properties means P, T, VUHS, and now we also know CP and CV are also thermodynamic properties. Anyways, so if you know any two of them, you can find the rest, and that's what we're going to do in the next few modules, how to figure out all the other rest of the properties if you know just two of them. And once you know the thermodynamic properties, then if you know the extrinsic properties are found, if you know, suppose you know the velocity and the height, then immediately you can find kinetic energy and potential energy. You know the formula, Ke equals what? V squared by 2000, and Pe equals Gz over 1000. The 1000 appears because the unit is kilojoule over kg. So just to remind you, where does this come from? We know capital Ke equals mv squared by 2000, so many kilojoules, and small ke equals capital Ke over m equals v squared by 2000 kilojoule per kg. Just to remind you, we have done that in chapter 1. So once you know the velocity and height, you can find all sorts of extrinsic properties, not only Ke, Pe, therefore you can find E, you can find J, etc. How? Because E equals what? E is nothing but Ke plus Pe plus Eu. So we can calculate that because U is a thermodynamic property and Ke and Pe are extrinsic properties. So therefore, E is also an extrinsic property because it contains an extrinsic component. And J similarly is Ke plus Pe plus H. Again, if you recall the definition, so J, E, etc. are extrinsic properties. And finally, you can find system properties if you know the mass for a system state, how? Suppose the mass is known, therefore what is the total energy? It will be mass times E. What will be total EU? Mass times U, specific. What will be total entropy? Mass times entropy, etc. Suppose you want to know the transport properties for a flow state. Recall the black properties in our extended system diagram. Transport properties for a flow state similarly can be obtained. How? Suppose you want to find J dot, it will be m dot times J. Suppose you want to find how much entropy is carried by a flow, it will be m dot times S, etc., etc. Or how much kinetic energy is carried by a flow, it will be like that, which is given by the transport equation. So I'll stop here, and we'll build on it different material models on what we have covered just now.